So this is a talk about effect systems. But before we get into effect systems, I just want to look at a piece of code. So this code is parsing an HTTP request. It's first looking at the method on the request, seeing if it's the method we're looking for, the method we're expecting. That's the HTTP verb, like get or post. If it's not, we raise an error. And if it is, we continue on with the next bit of the parsing. So this is fairly typical code like you would write in an imperative language, like Java or JavaScript. This is code that I wrote using an effect system in Scala 3. And my goal for the talk is for you to walk away from this talk saying, this is functional programming and this is good. So, if I'm making statements about functional programming, I first need to define what I mean by functional programming. So that's the first bit we'll do. Define functional programming. Then we're going to look at effect systems, see what they are, how they work. Next, we'll compare them to monads. And then finally, we're going to look at some of the things that effect systems are going to bring in the future when they're more widely available. All right. Quick question, actually. Has anyone used an effect system here? Okay, a shocking number of hands are going up. That's really interesting. I was not expecting that. So we'll see if you agree with me when we get to the end of the talk. But let's start by saying, what is functional programming? So if you ask people what functional programming is, you're likely to get a range of different answers. You get the people who say, well, the clue is in the name. It's functional programming. It's all about functions. Okay, I mean, that's one answer. Other people say it's about programming practices like using immutability, immutable data. You might get talk about language features, algebraic data types, monads, functors, all these kinds of things. And some people will mention concepts like purity, pure versus impure code, referential transparency. And people outside of functional programming, and some of those inside as well, will say, well, it seems like it's really just about fancy words. And those are all answers, but they don't really answer why. Why do we care about these fancy words? Why do we care about purity or referential transparency? Why do we use immutable data? What's the deal with first-class functions? And, maybe just like difficult things. I mean, I think we all like learning because we're at this conference and learning sort of turns difficult things into easy things. So perhaps that's what it's all about. Or maybe just like sounding smart, using all these big words. I mean, it's kind of true for definitely some parts of the functional programming community. But again, I don't think it gets to the actual core of it. And I think there is a reason behind all of these, and I want to dig into that reason. And this is my belief that functional programming, what it is at its core, functional programming is a hypothesis about what is the best kind of programming to do, what is the best way to program. And FP's answer to that is programming should emphasize reasoning and composition over other criteria. Okay, so if we take this as what functional programming is about, then we have to define reasoning and composition. So let's get into those. So firstly, what is reasoning? Well, the core idea of reasoning is just working out what code does. That's something that as developers we do all the time when we read code. And one of the goals of functional programming is to make this process easier. Spend less time at the address book, more time fixing problems. So there are different ways that you can reason about code, and the way we like to do it in functional programming is, as I said, reading code. So it's like code, we want code that we can actually read and figure out what's going on, as opposed to looking at it, the code that is running in a debugger, say. So functional programming is really about static reasoning with the code as written rather than reasoning of the code that is running dynamically. And the other big idea I said was composition. And what does composition mean? Well, informally, the idea of composition is building big things from small things. So it's like how Lego works. If you've played with Lego, I'm sure everyone has. You've done composition. If you've done functional programming, you've certainly done composition as well. Composition in parser combinators, for example. Composition in effect monads, if you worked with IO monads. Composition with numbers. Numbers composed with operations like addition. 1 plus 1 is 2. That's composition of two numbers into another number. Composition of the functions in functional programming. Function composition. So that's what composition is all about. And they are interconnected. Reasoning, this kind of static reasoning in particular, and composition go together. So let's have a look at how that works. Before we do, so the point here is that I'm saying the FP practices we have, immutability, and so on, these are all in the service of reasoning and composition. Now let's go into a bit of mathematics. So we want to look at how reasoning and composition are interrelated, and we're going to do that by looking at something called substitution. People heard of substitution before? Kind of curious. I have. Yay. Okay, a lot of hands going up. The fact is, all of you know substitution. It's something you learned in primary school, something that my children learned in primary school, although they weren't told it was substitution. So as a typical for functional program, we have fancy words, but we have simple ideas under it all. So we'll see that in a moment, what substitution is about. The first thing we need to have to talk about substitution is to talk about definitions. So let's define what we mean by a definition. When we write something like let x equals e, what we're doing is we are defining or binding the name x to some expression e, say in maths. Okay. And the next thing we need is actually substitution itself. So what does substitution mean? Well, there are sort of a few different substitution rules, but the one I'm going to focus on here is just this one that tells us when we see in an expression a reference to a name, we can replace that reference to the name with the expression to which it is bound. All right. Fairly abstract, lots of words. Let's see an example of substitution in practice. So if we have let x equals 2, and then we say let y equals x, what substitution says is when we have a reference in an expression to a name, and that's the x on the bottom there in blue, we can replace that with the value to which that name is bound. So we can replace it with the 2 to which the x above, highlighted in blue, is bound, giving us the following, let y equals 2. So those of you who hadn't heard of substitution before, I guarantee that you actually knew this because, like I say, this is taught really, it's really basic mathematics. That's taught in primary school, or maybe a little bit later in the beginning of high school in algebra. And you might say, okay, this is all nice in maths, but what about in programming? It doesn't apply in programming. So we can take this idea and apply it to a programming by changing the way we render the example, and we're going to render it as code, and now we have an example of substitution working in code. It works exactly the same way. Let x equals 2, let y equals x. There's one problem with this code. Does anyone see the problem? Okay, the problem is this is JavaScript. So we're going to change it to Scala, change all the uses of let to val, and we have this instead. It's much better now. You can agree? All right. And so substitution. We all know substitution, and substitution is really easy to work with. That's why we can teach it to young kids, because it's really simple. So this is the point of substitution. Substitution is really, really easy to reason with. It's really easy to understand what's going on in that static way that functional programming is like when you can use substitution. And that's why we like substitution in our programming languages. Now, substitution is also compositional. So let's see an example of that and what that means. So here we have an expression. We're back in mathematics land. So let x equal 1 plus 2 plus 3 plus 4. And what composition means, or compositional means, is that we can take the independent components and we can understand them independently and then combine them. And in this case, it means we can evaluate the expressions in the brackets independently. One expression in one set of brackets doesn't change the meaning of the expression in the other set of brackets. So we can do the usual maths we're used to. By 1 plus 2 and 3 plus 4 gives us 3 plus 7, and then we get 10, right? And there we composition. Right, all pretty straightforward stuff. We all know that even if we don't know the fancy terms that go along with it. Now, there's a problem here, which is that state and other things that we call effects break substitution. And what I mean by that, well, let's say we have this program here. written in Scala. And now instead of having an immutable value for x, we have a variable, a value that can change. And we are changing it here, x equals 3. And if we do naive substitution, we say, okay, what is x bound to? It's bound to 2, so y is equal to 2, then we get the wrong answer. So this is a problem. And it's a problem for reasoning because it means you can't look at bits of code in isolation. You have to know all of the code that could possibly change something you're looking at. So when you look at one piece of the program, you need to know the entire program, actually, to say, does anything change something I'm trying to reason about here? So when we have this kind of state, we don't have this property that's sometimes known as local reasoning. I mean, you can look at bits of code in isolation. So, yeah, we don't like state, it's a problem. So we talked about some of the practices of functional programming, like immutable data and so on. And these are all here in support of substitution. Substitution is the goal, and we like substitution because it gives us reasoning and composition. It's guaranteed. If we maintain substitution, as we say sometimes, then we can reason about a code in this very simple local way, and we get the composition where we can combine independent parts of our code and we know they're not affecting each other. So that's what I think is the core of functional programming. All right. Okay. So now let's talk about effects. What actually is an effect? I haven't really defined it so far, but now that we've talked about substitution, we can actually define what do we mean by an effect. Sometimes we say a side effect to distinguish it from kind of effects we might talk about in effect system world, functional programming world. So what I mean by a side effect is just something that breaks substitution. We've seen examples of state already, and we get the same things with, say, input and output, because when we read from a file, there may be different data at different times when you read from it. Or when we have something like an exception, it's a non-local control flow. You can't use substitution anymore because your program's not executing the bit you think it is, that jumped over to somewhere else. So these are examples of effects, and that we can define them in terms of substitution. There are things that mean that substitution doesn't work if they're present. The problem is that there is no useful program you can write which is going to avoid an effect. Even if your program is the most kind of, I don't know what to say, the most boring thing in the world is what I want to say, but maybe I shouldn't. That just calculates this one's output. You still need to be able to see that output. You still need to have that output actually somewhere you can see it. And then there are many more programs, interactive programs like computer games or the slides that I'm scrolling through now that have to interact with the outside world. So you can't write a program without some kind of effect. At least you can't write a useful program without some kind of effect. So we have a problem. And now let's look at effect systems, and we'll see how effect systems solve the problem of integrating effects into the functional programming world, where we're trying to keep these properties of reasoning and composition. All right. Okay. So I think the core idea in the world of effect systems is that we break effects into two parts, which are called the operations and the handlers. Sometimes operations are just called effects. The handlers are normally called handlers. And operations are just sort of descriptions or interfaces to effects that we want to occur. Here's an example. So this is an example in the code I showed earlier. We had this operation called raise, which raises an error of type E, whatever that could be, change depending on the context. And the return type of raise is nothing, indicating that control flow goes somewhere else when we raise an error. It doesn't return to the point where we call raise. So this is an example of the kind of operation we want to implement. It's probably familiar because I expect almost everyone here has programmed with exceptions at some point, and you'll see that raise is the analog to throwing an exception. Okay. Now, how do we use these operations? And one of the things about effect systems is that using them is just normal code. So we might write something like this. Well, you need to give me an implementation of raise, and then I'm going to call it at some point. Here we're checking if we have a points failure, which is something that's very common on the UK rail system. People know about points failures. I've always been kind of baffled and horrified by this understanding that Euclidean geometry could fail at any time when I'm walking, or I'm not walking, when I'm sitting on a train. But apparently it happens all the time in the UK, and we don't notice it. So let's program that's using an effect operation. Now the other part are the handlers. What do the handlers do? They actually provide this non-local return in the case of arrays. And so an example would be something like this. Handler, we've got a load of Scala syntax here, which is not really important. The important bit is we have this apply method that says, give me a function that needs an instance of raise, needs a value that can raise things, and I will give you back some representation of the errors and the values it can return. And that representation, we're not tied to any particular one in this code. It could be like a sort of IO monad, it could be an either type, or it could just throw away the errors, or it could throw away the successors. It doesn't commit to any particular representation. And it's quite useful to be able to have different choices in different parts of the code. We also have another method in here, succeed, which is useful in practice, but it's not really important to the main thrust of what we're talking about. The core idea is just that the handler is just giving us an implementation that does whatever it chooses to do as appropriate. Now, what do you get from this system is we get this idea that effects can happen up to the point where the handler is applied. So outside of the scope where the handler applies, reasoning is easier because you're back in this world of substitution. So I think we have an example here. So we have the code at the top. We know A and B, this is just pure code. And we know that effects can only happen inside the spots where we have declared that effects can happen, basically. So the handlers delimit points where the effects stop. They put this boundary, and they isolate the effects within it, and we have the types showing us where the effects can happen and where they can't happen. Let me just say one point here. So this is nice because it enables us to reason relatively clearly. We can tell effects happen in here. I have to reason in a different way. I'm not in a context where effects can happen. I can reason using substitution. Right. Another thing we have here is that programs that use the operations, the effect bits, are themselves functions requiring the handlers. And what this means is that they are descriptions. What do I mean by a description? Well, some of you will have heard me say this before. But as a description, they are things that describe what they want to happen, but they don't actually make it happen until the handler is applied. And therefore, they can be composed. In what the code I've shown, they are functions. And I have here an example using an effect which can print something. It's a function. We can compose functions using function composition, right? But if you have the action itself, like just the raw printing something to the console, you cannot compose that. And the reason you can't is because as soon as you evaluate that, the action happens. There's no possibility of sort of grabbing hold of the action and changing anyway. All you've got is the unit you get back from calling that print line. So there's nothing to compose there. Whereas functions, this description, describing the action on happen, is something that we can compose. We can pass it around, and we can substitute freely with the descriptions. So that's nice. All right. So summary. We have this isolation of effects that tells us where we can reason using substitution and where we cannot. And we have this separation of description actions. And when we're working with descriptions, again, we can freely substitute descriptions and pass them around and compose them. So we get compositionality and reasoning in this way from effect handlers. Okay, so that all sounds nice, I guess, but I need to address the burrito in the room, and that is monads. How do effect handlers compare to monads? Let's have a look. So I guess most people are familiar with monads, but to recap, or if you're not familiar with the way Scala uses monads, we're going to define them in terms of this function flat map, which is the most important part of a monad. I know the monad also has to have pure and the laws associated with it, but that's not important for our context. And flat map is a function from A to f of b. So we have some input of type A, and we return a type B wrapped up in some type F, and that F is the monad. And if you come from the Haskell background, this is bind, or as Haskellers love to write cryptic code, that little arrowy thing. Right, the problem with monads is they change how we write code. Here, at the top we'd have code as we'd normally write it if it was pure code, but if we have to change it to monads, then suddenly we invert it all using flat map. We have to chain all these flat maps together. And that is kind of annoying. And monads force us to basically invert the control flow. Suddenly everything sort of shifts to the right-hand side. And that's a bit of a problem. It's a problem, you get used to it, you learn how to write it, but it's a problem to onboard new people. And I think this is a conference with people who are interested in industry adoption of functional programming. And definitely one of the issues we have is teaching people. They come knowing a set of concepts, and then we pile a whole bunch of new concepts onto that. Anyway, this style of writing code is known as continuation parsing style. There have been a few talks already that mention continuations. There's one about Kotlin. So this idea is coming up in different contexts. Maybe interesting to see here. There's definitely a deep connection. But I'm not going to go too far into continuation parsing style here. However, what I want to say is contrast to effect systems. With effect systems, we just wrote normal code. There was no need for this continuation parsing style. And we call this direct style. Direct style is a name for just normal code, just code as we'd like to write it. So that's one comparison. Monads, we have to do this code transformation, which is continuation parsing style. Effect systems, we just work with direct style. It's easier to do. What about the isolation of effects that we saw in effect systems, and what about the separation of description and action? Well, effects in monads are isolated to some extent. We know that effects happen within the monad, and we know they don't happen when they're outside the monad, if we write our code correctly. I don't find this as powerful as effect systems in practice. And the reason for that is twofold. One is that practical effects in monads end up using just sort of one IO monad that doesn't really give you much granularity in what's going on. You can write code in tag this final style, tag this final style, they're right. Or with monad transformers, but they have their own problems. Tag this final is quite tedious to work with. Monad transformers, again, are also tedious in different ways. So I don't feel like this approach is as good as it is in the effect system world. And also, once you introduce monads, they kind of tend to spread to the rest of your program. So you end up just adjusting your program to return the monad everywhere. And I think most practical systems end up with just large parts of the code just working in the monad because it's easier. So I don't really feel like we do get some isolation in monads, but I don't feel it's as useful as effect systems. Effect monads are definitely descriptions. They definitely have this distinction between description and action, and the whole programming with values type of thing, substitution, that works. So that's all fine. So if we summarize them, we get this. Unsurprisingly for this talk, effect systems win on all counts. So monads and effect systems are equivalent in the separation between description and action, but I find effect systems better for isolating effects, allowing me to know where I'm inside the effect and when I'm outside. And in terms of the style of code, I find the direct style of effect systems much easier to write than the convoluted CPS style that I have when using monads. Okay. So monads, weird code, get some benefits. Effect systems, write normal code, get all of the benefits. To me, it's pretty straightforward. And now let's just note that one of the differences, and I think one of the complaints that some people might have about effect systems is that you write this code when you have effects that looks like imperative style code. Like the code I showed at the beginning had this thing that looked like we're throwing an exception. And whilst I find that reasoning composition are really big wins in large bits of code, massive wins, I do want to do that without them. I do find that reasoning about imperative code is not too hard when that code is restricted. We can all do that. I imagine you all reasoned about the code I showed on the first slide without problems. So it's only when that code becomes large that the reasoning becomes an issue. And with effect systems, we get this isolation. And here's a simple example, not using the effect system, but I just want to illustrate this point. Here we are summing up all of the elements in a list. We have some mutable state, that is the total. We just go through the list, add the elements to the total, return the total. And there's some things we should note about this code. One, it's easy to reason about what it's doing inside the method. And two, from outside, the fact you use this state is completely hidden. We can reason about this method or function as if it was pure from the outside because it doesn't expose the state in any way. And effect systems are already just taking this idea and formalizing it for a large quantity of effects, more than just functional method local state like we have here. Okay, how are we doing? So now I want to talk about how effect systems are implemented and look at some of the things that they bring us, because I think they actually do give us some new capabilities, which are really exciting, but it's getting more into the research world. So the two things that go into effect systems. Fancy type systems, which we all love. I've avoided talking about the type systems so far because I didn't want to talk about specific types. Type systems, we do that a little bit, and then the runtime support that goes into making effect systems work. So yeah, type systems are still active research. There's lots of papers published about the different type systems for effect systems. It's not at the point where we have like a generally agreed upon implementation strategy or set of features like we do for, say, algebraic data types or type classes. Different languages support different things. So I can't say much that would generalize across different languages here. I'm going to talk about Scala 3 because that's the language I'm most familiar with. OCaml, Unison have effect systems in slightly different ways. I'm actually curious, of the people who put their hand up having used an effect system, have you used Scala 3? I put my hand up. Okay. A lot of people have. Used Unison, say, it has an effect system. 1 hand, 2 hands, half a hand, 1.5 hands. What about OCaml? Which is 1 hand, okay, 2 hands, 3 hands. Okay, so most people here are familiar with Scala 3. So that's good. So Scala 3 has this currently experimental feature, which is going to be unexperimental at some point in the future, called capture checking. And this is a core part of making the effect system work for real across all the effects we want to do. And what does capture checking do? Well, what it means is that the type system ensures that a section of code will hold no references to a value when that section of code exits. We have an example here. So this looks like pretty normal code, except where we have the file defined, the type has a little caret, little arrow next to it. And what that means is that the function f is not allowed to capture the file that is passed. So that means when it exits, when that function returns, it can not have a reference to the file anywhere, and that in turn means it's safe to close the file when the function returns. So we can write this type of code, open the file, pass it to the function, get the value back, and close the file, and it's safe because we've ensured there's no reference to that file and it can't try to write to that file once it's exited. So that's what capture checking does. Not particularly exciting in this example, although it is pretty neat. But one thing that I find personally really exciting is we can implement region-based memory allocation with capture checking. What I mean by region-based memory allocation, that's a great question. It's sometimes known as arena allocation. And the idea with a region-based memory allocation is you allocate a chunk of memory, known as a region or an arena, and then part of your program uses that arena, allocates the memory it needs from that arena. So why do we do this? Well, getting a big chunk of memory from the operating system is generally pretty fast. And then you usually use region-based allocation in a single-threaded context. And allocation within the region, the single thread is really fast because all you're doing is incrementing a little pointer where to allocate next. And we can implement region-based allocation in the same way we did with that file. We just change the words a little bit. So we say f now gets a region it can allocate things from, but it can't hold any references to that region when it's finished. So we know when it returns, there are no references left to that memory. We can free the memory, give it back to the operating system, and no leaks, no memory leaks there. And I think that's really cool. You probably all know about Rust with its approach to memory management. You know, it has the borrow checker, and there are definitely issues around the ergonomics of using the borrow checker. What we have here is not quite the same approach because it's working at a region, not on the individual level of values. You couldn't make it do that. It wouldn't be very practical. But it gives you a lot of the benefits of what you would do with manual memory management, but in a system that works with other parts of the language. So we don't have a special system just for this. We have this capture checking, which works for our effect systems in general. So you don't have to learn specific rules of borrow checking. You have to learn the rules of the capture checking, which I think is quite straightforward. No references allowed. And it gives us this very ergonomic way of doing something which is considered quite low-level system programming. So I'm really excited to see what we do with system programming and effect systems in the future, because I think they could give us a much more ergonomic way of doing memory management in high-level languages than we currently have. All right. My screen just went blank. Let's see if we can come back. Okay. Yeah, we're back. Okay. Now let's talk about the runtime a bit. So I've talked about type systems and the things they allow us to do. Let's talk about the runtime. So I talked about continuation parsing style, and these sort of continuations haven't gone away. The runtime for an effect system needs to support capturing continuations and invoking them. So these continuations are still here. They're just hidden away under the hood. And it's actually really good. So one thing, it gives us better performance because it's implemented by the language itself rather than being a level on top of the language implemented by the Monad implementation. So that's there. And the other thing is you can do really fun things with continuations. And one of the things you get with continuations you have to get is full proper tail calls. And if you're a functional programming industry, this is the thing you've been yearning for forever because most languages, most runtimes don't support tail calls, but there's so much you can do with them. There's so much of functional programming, the patterns are based around tail calls. We have to do a lot of work to get around the lack of them. So lots of fun things available there, and that's pretty exciting to me, and better performance. Nice stuff. All right. So that's what I want to say about effect systems. Before we go, let's just say shout out to the person who provided the photo of Cádiz that I used on the front page. And I hope you now agree that the code I showed earlier is functional programming, and it is good. If you don't agree, maybe talk to me afterwards. Find it out. But have any questions? I'd love to take them now. Thank you.